Hi everyone, and welcome to this video on energy and momentum in space. We're going to look at two main things in this video. The first thing we're going to look at is rocket propulsion, and the second thing we're going to look at is this idea of gravitational assist. Now you can see from the picture below that this is a completely impractical example, but it will help us understand a little bit about how rocket propulsion actually works. What we can do is we could be standing on a cart that is free to move, and if we had a bunch of cannonballs and a cannon on that cart, we could start shooting the cannonballs off the back end of the cart. What that would mean is that our cart would begin rolling in the opposite direction. This has to do with Newton's third law. Every action force has an equal and opposite reaction force. So in other words, there is an action force of the cannon on the ball, and there's a reaction force of the ball back on the cannon. And so if we could use the impulse and the force that the ball is exerting on the cannon, we could then turn around and figure out the impulse and force that the cannon is exerting on the ball. And that would allow us to figure out how fast we would accelerate backwards in this case. Now that is analogous to a rocket, as you can see below. Let's just draw the forces that are acting here so we can see how this works. On the ball, we could say there's a force, and there's other forces beyond this, but I'm going to focus on the force of the cannon on the ball. The force of the cannon on the ball. On the cannon, and on the whole, in fact, if the cannon is attached to the cart, there's a force of the ball on the cannon. Now, I've drawn one longer than the others, but those are actual equal and opposite forces. And so because the ball is less massive, it's going to accelerate much more quickly than the cart will. But nonetheless, because it does have some mass, the cart will accelerate at some acceleration backwards. That is analogous, as I already said, to a rocket ship. And so we can think about two things happening here. The first thing is we have some gas, and that gas is experiencing a force of the rocket ship, we'll say rocket ship, on the gas. And on the other thing, on the actual rocket ship, that's experiencing a force of the gas on the rocket. And so this is equal and opposite to this force, and the force of the gas on the rocket is what we call the thrust of the rocket. So let's go ahead and just derive some of these equations for this. The McGraw-Hill-Ryerson derives this in terms of impulse, but I'm going to derive this equation in terms of Newton's second law. We can derive it both ways. And so what I'm going to do is I'm going to start with the force. We know the Newton's second law says that the net force is equal to mass times acceleration. Well, what I want to focus in on here is the force on the gas. So the rocket on the gas. This is what I'm going to put it in terms of. So I'm going to go the force of, or on the gas is how we're going to write this. It's the rocket on the gas is equal to the mass of the gas times the acceleration of the gas. Now, that's all well and good, but how do we actually get this in terms of change in velocity and time? Because that's what we really need in terms of. Well, acceleration is the change in velocity over change in time. And so what that gives us is it gives us, if we just rearrange this slightly, that the force on the gas is equal to the mass of the gas divided by delta t times the change in velocity. We're going to put this in brackets. We're going to put it in brackets because mass of gas divided by delta t is the rate of combustion or the rate of flow of the gas. And so what we have is a rate times change in velocity, and that gives us our force on the gas. Notice that this is the change in velocity of the gas. The change in velocity of the rocket ship is going to be very different because it's going to have a much greater mass than the gas that's being burned off in a given amount of time. Now this force on the gas is the force of the rocket on the gas. It is the action force in this action-reaction pair, and this is referred to as the thrust. Thrust specifically is defined as the action force of the gas coming out of the rocket. Action force of, maybe better put would be the rocket on the gas. The action force of the rocket on the gas is what thrust is. And so when you hear someone say that this engine has a lot of thrust, it means that there is a great amount of force from the engine on the gas. It's worth noting a couple things here. One is that the rate of flow is sometimes referred to as the burn rate. And a second thing worth noting is that this change in velocity of the gas is referred to as the exhaust velocity, because the gas is the exhaust. So let's go ahead and solve and do one example together of this. So this question asks what burn rate of gas, and remember burn rate is the rate of flow, and so this is in terms of the mass of the gas divided by the change in time. What burn rate of gas is required if gas with an exhaust speed of 2,500 meters per second is to give a thrust of 15 meganewtons. Mega meaning 10 to the power of 6, and newtons because the thrust is always a force. So we're trying to figure out what that burn rate is. We know that the exhaust speed, assuming that gas starts in the rocket with no velocity and then it's shot off with an exhaust speed of 2,500 meters per second, that means that the change in velocity of the gas is 2,500 meters per second, and that's going to be backwards because the gas is being shot in the reverse direction as you're trying to travel. The thrust is the force on the gas. That is going to be 15 times 10 to the 6 newtons, or 1.5 times 10 to the 7 newtons if you wanted to put it like that. But it's correct to say 15 times 10 to the 6 newtons as well. Now all we need to do is go ahead and start with our equation that we've derived for this. The force of the gas is the mass of the gas divided by the change in time times the exhaust velocity. And you'll notice that if I multiply both sides by the change in velocity, rather divide both sides by the change in velocity, that's going to cancel off this side. And if I divide this side by the change in velocity, what I'm going to arrive at is something that has my burn rate right here, and it's equal to the ratio of the force divided by the change in velocity. So my burn rate is equal to that ratio divided by the change in velocity on the gas, and that is 15 times 10 to the 6 newtons, because mega means 10 to the 6. And in the denominator, we get 2,500 meters per second. Now, this does not depend on direction, so that's going to cancel out. And what we're going to be left with is 6.0 times 10 to the 3 kilograms per second. Well, how'd you get units of kilograms per second? Well, this is a newton divided by a meters per second. And remember, 1 newton is 1 kilogram. If you think of Newton's second law, it's 1 kilogram, so it's a mass times an acceleration divided by 1 meter per second. So meters cancel out, the second cancels out with that second, and we're left with units of kilograms per second. In other words, that means that the burn rate must be 6,000, 6.0 times 10 to the 3 kilograms every second. We're talking tons of gas. This is actually a realistic number in terms of burning fuel to get into space off of Earth. We're talking 6,000 kilograms a second of gas is actually being burned to get this to actually happen for this thrust. There's a great example in your textbook, a sample problem in section 6.3, which goes over this as well in detail and should help you out with the questions that you have. If you have any further questions, please reach out and don't hesitate to ask.